yeah, like we're a ABC blockchain community. Why we call it ABC? Because if you take the initial letter of each word out, you'll see like A, B, C again. So it's like GNU, it's a recursive definition. And these three keywords are like the thing like we're focused on. First, we're a non-profit organization, so we're neutral to all projects and capitals. And second is we are technical focused. All our events, including like workshop, tech talk, white paper journal club, that kind of thing, they were like technical focused. So we don't talk about the price of the coins or the price of tokens during the meeting. Okay. So the third is don't be depressed. Okay. The third is mission driven. So our mission is to like unite the enthusiasts and talents of the blockchain industry to make the world like more transparent, more efficient, and more collaborative. So yeah, that's kind of abstract goal, but we're like pushing forward this goal by holding these kind of events and gathering all the experts from like in the blockchain industry, you know.
So hello everyone, I'm glad to be here. We started this Nervos, this project, with CMD together at the beginning of this year. So the Nervos founding team is include me, Terry, Daniel, and Kevin. And Daniel once worked for mToken, and Daniel was the co-founder of mToken. And so Cryptofriendly also built a mining pool before for ETH, and the mining pool is now the second largest Ethereum mining pool in the world. Its name is Spark Pool. So we have a lot of experience in this ecosystem. We have worked on exchange, mining pool, wallet, permission blockchain, and finally we turn to public blockchain because we think we have a brilliant idea of how to do it. So yeah. The idea is we know everyone is facing this trilemma, right? The trilemma of scalability. Like you can have all those three things, and you need to balance between decentralization and scalability, because no one will give up security, right? Except for some projects. I will not name them. So, so you need to choose, right? And there is a conflict in essence, right? Because no consensus is faster than no consensus. In distributed system or in blockchain, we need consensus. We need to agree on the order of transactions. And if we want decentralization, it means we want to have consensus agreements between a lot of nodes. And the more the nodes, the more messages we need to transmit between those nodes to reach consensus, which means you will have worse scalability. So it's a conflict in essence, and we need to face the fact. We need to face the fact that secure global consensus is slow and expensive. And in my opinion, it's not avoidable. So it's just decentralization is just always slow and expensive than centralization system. So in my opinion, the right way is not to try to make decentralization as fast as decentralization. It is not to try to make global consensus as cheap or faster as possible, but to invent some way or design some mechanism to work around, because that's a problem we cannot solve. So how to work around? We change the question to how to work around. We need to think in the other direction, because now if we like the supply and demand curve, right? If we cannot increase our supply, the only thing we can do is to decrease the demand and use the limited supply in the right place, in the most deserved place, right? We need to maximize the effect of the limited charts created by blockchain. We need to maximize the effect created by the slow and expensive blockchain, right? So how to maximize the effect? If you're thinking in the other direction, right, the best thing we can do with a blockchain is use it to hold misbehavior accountable, to enforce security of other layers. We can use it as a 威慑怎么说 threat. Okay, to other normal operations. Okay. Because if you think about normal things and abnormal things, right? Abnormal operations is the minority of all those things. Maybe 99% of our operations are normal, and only 1% of them are bad. And we only need to punish the 1% of the bad thing. The blockchain only need to handle the 1% to enforce all those 99% of operations are normal, are right. Right? That's the basic idea of layered network. Right? We want to push all those normal operations to another layer, layer 2. And on layer 2, it's easy to scale. And only when things goes bad, we ask operators or participants on layer 2 to submit all those proofs back to layer 1 and ask layer 1 to judge, to punish all those abnormal operations, to punish all those bad behaviors. And why this whole layer network will scale is because we move the majority to another layer. The majority of the actions, operations, transactions, they won't hit layer 1, right? If everything goes well, it just goes on layer 2. It doesn't need to hit layer 1. And only when things goes bad. Yeah.
I do have a question. I feel like you're shifted the responsibility of finding the bad, like abnormal operations to layer 2, right? So are you assuming like layer 2 is always reasonable and secure, so you can like find these bad operations and submit proofs to layer 1, right?
Yeah.
What if this layer 2 is corrupted itself?
Good question. Because there's competition in layer 2. Okay, because you can do bad things and you want to hide your bad behavior. But there are always other watchers on layer 2. There are other participants. They can submit the proof to layer 1, not yourself. Right? It's like the competition in POW. Right? Miners will compete with each other. So if we consider layer 1 in such a big picture, right? What should be the design goals of layer 1? Blockchain. I call it layer 1 blockchain, not blockchain, because it's a blockchain designed as a layer 1 in such a layered network. So it's easy to see we need the blockchain to be a store of assets. By store of assets, I mean user can create any kind of new assets as they want. So there are assets which can be used as collateral and which can be confiscated when bad things happen. Right? The blockchain must be a crypto court. By crypto court, I mean when bad things happen on layer 2, the participants on layer 2 can submit crypto proof to layer 1, and the court can make judgment based on those crypto proofs. Right? And it needs to be layer 2 friendly, so they can communicate with each other, interact with each other seamlessly. That's the basic design goals in my opinion. That's the design goals of Nervos CKB. Which is the,
So go to previous slide.
yeah.
So why there are no, so you did not set any decentralization or security on the layer 1 design goal?
Yeah, that's the basic thing. So I just ignore them. So we want to achieve all these goals. All these goals without lose decentralization and security.
Okay.
Yeah. So the idea of CKB is to be a minimum layer 1, which implements or achieves all those 3 goals. Okay? So we can start with the basic design, which is blocks, right? The blocks in CKB is basically the same, is not basically, exactly the same as those in Bitcoin or Ethereum, right? We have header, we have transactions, and we have like transaction Merkle root in header pointing to all those transactions in body. Right? That's the same. But we will face a design decision very quickly, which is when we try to decide the data structure of a transaction, we need to decide what kind of transaction semantic should we have of CKB transaction. Right. What do I mean by transaction semantic? So if we consider blockchain as a replicated state machine, the basic model of distributed system, right? In state machine, we have state or event, the 2 basic elements. So naturally, we have 2 options to model and transaction, which is the state transition of blockchain, right? We can have option A, which I call it on-chain state. By on-chain state, I mean in transaction, we have old state, event, and new state. All those data in this transaction. So the transaction includes all the information necessary or all the information for a state transition. Right? Even there are some redundancy in this transaction, but we just put all of the data in this transaction. Because the state, the new state, the result is included in the transaction, and transaction is included in block, which means the all those new states are on-chain. By on-chain, I mean included in block. Right? If you get a block, you will get those new states directly. You don't need any extra work. In contrast, we have option B, which is I can remove all those redundant information, only leave event in this transaction, right? Because I have previous state and now I have event, I can always calculate the new state. And the new state is being calculated by node and stored stored on node locally. And if you look carefully at this transaction and the state, you will find that all those states are not in blockchain. By that, I call it off-chain state. Any questions? Okay.
Is it option A, B, or C if you post a Merkle root of the new state, but only the event, where you don't print the. If I include in the transaction only the event plus a Merkle commitment of the
So
new state.
you mean yeah? So I'll say it's option B because now I have a Merkle root 2 states here.
Okay.
Yeah.
Okay.
But like in this case, you need to say on to restore the latest state, right? And like chain of events happening.
Mhm.
You are losing like you have to get any intermediate state. You have like rerun the whole thing, right?
Right.
This is what happened in blockchain, right? In the Bitcoin, right?
You guess?
Similar.
Yeah.
But they have the new state, right? You know, like the
I'm not sure they
output.
have it, but they don't record everything in chain.
Well, I'll give you guys a hint. So one of the options is Bitcoin, and the other is Ethereum.
Yeah, this is the Bitcoin, that is Ethereum.
So
Ethereum.
we can vote for it. Who think this is Ethereum? Okay. Who think this is Bitcoin? Okay. That's interesting because this is Ethereum.
Okay.
And on-chain state semantic is Bitcoin. Like this is input, this is output. And in Ethereum, even is the transaction.data field. Yeah. So yeah, so in Ethereum, all the full nodes need to calculate the new state by themselves. And what's transferred on network is not states, it's event. Okay. So when we want to design a new blockchain, we need to think about which option we need, right? So if we think about this question, and you'll find there are some features or characteristics of on-chain state option. Okay. The first one is on-chain state will naturally make your system a verification system instead of a computation system. Why? Because so in an off-chain state design, what I also call it event-focused design. The user trigger an event, and your wallet or full node will package or wrap the event into a transaction. In the transaction, it's event, right? And the event will be broadcasted, and miner will calculate new states, generate new state based on the event. So the state generation happens on full node, happens on minor node. But in a state-focused design or on-chain state design, also the user trigger an event, but the wallet or full node will generate the new state immediately on client side, and then package the reference to old state, the event, and the new state into a single transaction and broadcast it to a network, and the network will only do verification. So, for example, we can take a concrete example, okay? This is Bitcoin, right? User tells wallet how much coins I want to transfer, and wallet will do the computation, which is I need to find out all those UTXOs in my wallet and spend them and create new UTXOs and combine those spent transaction output and UTXOs into a transaction and broadcast the transaction. And what a full node or minor node do is only verification. By verification, I mean the minor node only needs to verify the sum of inputs equals to the sum of outputs. The verification process is completely different from the generation process, because the generation process is search in your current UTXO set and generate new UTXO. But the verification part is check if the sum is equal, right? That's two different parts. But in Ethereum, it's different. Your wallet won't do the calculation. Your wallet will only send the transaction to a full node, and the full node will do the calculation for you. Okay. So why is this important? It's because if you have a verification system, you will naturally have two layers. Layer 1 is the verification system, and layer 2 is the generation system. It doesn't matter if the new state is generated by a new wallet, by a wallet, or by a web server, or by a state channel, or by any like multi-party computation, or by plasma chain. I don't care how this new state is generated. the layers will be separated naturally. Layer 2 for generation, layer 1 for verification. This is a natural result of on-chain state design. Okay. And there are another property of on-chain state is, I think it's more layer 2 friendly. Why?
Especially for the smart contract.
Yes. So, yeah, why? Because it's light client friendly. Why is it light client friendly? It's because all those states are in the blocks, and all those states, new states, are in transaction, right? As a light client, I just need to receive all those new transactions and filter out all those transactions I don't need and keep all those state I'm interested. Right? It's easy to do such things in a on-chain state design, but hard to do it in a off-chain state design, because if you think about it, when I get a transaction include only event in it, how can I know it's related to some state I'm interested in? Right? I don't know which part of state in the world state the event will touch, right? Because the event may cause a smart contract to call another smart contract, to call another smart contract, to call another smart contract. And I can never know which part of state the event will touch without really executing. Right? That's the hard part of, that's the unfriendly part of light client unfriendly part of off-chain state design. Okay, so because it is light client friendly, which means the layer 2 participants only need a light client to participate in layer 2 protocols. Then they only need to keep partial states. I think it's good for layer 2. Okay. So it's like these are the states in a blockchain, and I only need to care about these blue ones. Okay, so that's the reason we use on-chain state in CKB. By the way, CKB is a layer 1 in Nervos network. Okay, because a verification system is enough for our design goals. It's enough for store of assets and crypto court. It's because separation of generation and verification aligns with the separation of layer 2, layer 1. Okay, and because it's more layer 2 friendly, and with all those parts, they form a closed loop to reinforce each other. Okay, we started from a layer network design goal, and we go for on-chain state, which causes the natural separation, and which leads back to layers. Okay. So in CKB, we call our state model based on on-chain state idea cell model. We call it cell model. Now I'll give give you more details on cell model. So first we check the transaction in CKB. Okay, it's quite similar to Bitcoin transaction. Transaction in CKB has inputs and outputs, but it's not like coins inputs or and coins output. It's old states as input and new states, general states as outputs. And transaction are just inputs and outputs. And inputs reference to previous outputs, as in Bitcoin. And if we enlarge and check it in detail, the input in a transaction is actually a reference to a previous cell and an event as input. in event we can have user input or witness to a log script. Okay. The new state is a new cell. Cell is the minimal state unit in CKB. Cell is just a piece of memory, a piece of data. And in cell, we have three simple fields. The first is capacity. Capacity means how many bytes we can save in this cell. And data is a binary field. User can store any binary bytes in this field. And log script is like the script in Bitcoin. You have a script to authenticate the owner of this cell, to protect this cell, which means cell is basically a piece of data with ownership. Right? The only way to update the data in the cell is you provide some input or witness or signature in this event to make the log script returns 0 to returns true. Okay, then then the transaction is valid, and then you can update old data in this reference cell and create a new version of this cell.
So which means the log script owning is kind of permission configurations based on Bitcoin script language.
Not Bitcoin script. I'll explain. So you basically you can write any code here to express any kind of authentication or authorization rules.
Okay.
Okay. So the only rule here is all the bytes add together. The length of the bytes must not be greater than capacity. Okay. Which makes capacity the native asset in CKB. So if you own some capacity in CKB, you can use it to store state. Okay. This is the native asset. Okay, now we have transaction and how to verify a transaction. Right. In Bitcoin, we have very simple rules, which is you can the transaction is valid if you have right signature to in input, and the sum of inputs equals to the sum of outputs. Right. But here we generalize it a little bit. Basically, the verification rule is this: for every input, if this evaluate to if this evaluate to 0, the transaction is valid. Right. For every input, I evaluate the log script from this referenced old cell here. Right. I use it as the code and use the user input and all inputs and outputs as data, as arguments to this script. And if the script evaluates to 0, the transaction is valid. This is quite a quite simple verification model, right? It's similar to Bitcoin. It's just we just add generalized Bitcoin a little bit, not much. Right. So in essence, CKB is a generalization of Bitcoin. Like we add a little thing. We add this data to UTXO because amount is always an integer. Yes, please.
So if I want to represent a contract, it will be a threading of states. So how do I track the contract? Is it indexed in some way, or that I want? So can I associate some kind of identity to this state so that I can track, oh, this is the state of my contract, and then I can use that as an input for the further thing?
Yeah, actually, we may not build such a mechanism in the underlying layer. We want to allow users to build it on top of our virtual machine.
Okay.
Yeah.
Quick question.
Yeah.
So if we're doing this way, is that efficient to store the data? Because it looks like you have to keep track of each version of the data.
Right.
So many
Is
replicas.
that
Right.
efficient?
I think it depends. Depends on what metrics you are using. Efficient in what way? Because if you, this is basically like an analogy for this is, it's like Git versus SVN, right? Do you think Git is efficient, right?
Yeah.
Yeah.
That's
Basically,
simple.
the state on-chain state version is Git, and the other is SVN.
One question here. So when you mentioned that you are going to leave the question of the state to the users and implementing the VM, are you saying the VM has a state?
Which slide this?
Here, right. So you just when you just answering this gentleman's question, you were
Mhm.
saying that the state of the smart contract is to be implemented by the user, right?
I mean the identity mechanism. I want to leave it to users. So you can have identity of a contract, and user can call the contract using that identity. Yeah. Yeah, I'll have more explanation in later slide. Yeah, so it's a generalization. So yeah, we choose on-chain state. Okay, now we turn to CKB VM because in previous slide we use CKB VM to evaluate the script, the log script in cell, right? So CKB VM is simple yet powerful. It's basically a RISC-V simulator written in Rust. We wrote it from scratch. And why we use RISC-V? We did a lot of research in like all kinds of solutions like WebAssembly, EVM, x86, RISC-V, and we choose RISC-V because it's very, very simple. Like the core instruction set has less than 50 instructions, and even the EVM, which is a very simple VM, has 74 opcodes, and not mention x86, right? And it's simple, but it's also powerful because it's a open standard joined by a lot of giants like Google, Samsung, all those chip manufacturers. It's a open instruction set designed for chip, designed for hardware, which means it's stable. The core instruction set has already been fixed, which means we will have no hard fork risk in future. If the standard is constantly changing, we need to hard fork ourselves to keep compatible with the standard. But an instruction set is designed for hardware. Think about it, right? They won't change much. That's why I think that's a very, very large benefit of RISC-V. And because of all those supports from industry, it has awesome industrial support. The available toolchains today include GCC, LLVM, and a lot of others. Why is this important? Okay. Come back to our cell model. It's because we can have libraries in this system, because code is state and state is code. Like in a cell, in the data field of a cell, we can put code in cell's data, right? To make the cell to be a code cell or a library cell. And you can use some instructions to load this piece of code into memory and execute it. Okay. So this, which means you can deploy, you can build library and deploy the code of the library into a cell and reuse it in other cells. Questions? Okay, so now imagine the library is a crypto library. Okay, we can have any crypto primitive, like most of them are written in C, and we can compile the C library into RISC-V instructions and save those instructions in a crypto library cell, and use any crypto primitive in my log script. This will make our system very crypto friendly, right? Because now we can add crypto primitives as library. We have benchmarked SecT256K1 ourselves. We use Bitcoin Core SecT, and we changed the 0 line of code. And it took only 27 milliseconds to verify a signature on a barely optimized CKB VM. It's not bad because we haven't do a lot of optimization yet, and this latency means we can have like 20 transactions per second for 2 input, 2 output transaction in CKB with a crypto primitive running on our VM. We can have no crypto primitive in our virtual machine. We want to abstract all those crypto primitives into libraries in our system. And we think we can do a lot much better than this. There are a lot of space to optimize. And we are working on more optimizations to make it faster. This is only the first version of CKB VM. Question? Yeah.
Are you going to use a jet like Urbit or
Yes.
Simplicity? Okay.
So we have a crypto-friendly VM in CKB. And the third thing is Microstates. Again, the same picture, the same graph. We can have we can write our asset definition and save all the code in asset definition cell. By this, it basically means the code, the logic in a like ERC20. Okay, we use ERC20 to define new asset on Ethereum, and we can do the same thing in CKB and have the code stored in a cell. And what CKB is good for is we can have the state belongs to user in their own cells. So each user, like they'll have their tokens here. They'll have their state of tokens stored in his own cell. Right. Like this is Alice's asset cell. This is Bob's asset cell, and in Alice's cell, there will be a state related to only Alice's token. And in Bob's cell, the state is only related to Bob's token. So this is different compared to like ERC20, right? Because here is two different patterns of defining asset. In ERC20, you have all the logic of asset in a single contract. you have other authentication rules to allow user to transfer their or to transfer or issue new tokens. And all those states, no matter it's state of who, are in the same contract. Right. You have Alice has like 100 tokens, Bob has 200. But now we are talking about separate the code and the state. First we separate code from state. Then we split states into microstate, and each person has his own microstate. Now Alice has a cell, Bob has a cell. It's all separated. So in this system, cell is basically state with ownership, because the ownership is expressed with lock script, and each user has his own state. Use his own state to store all the relative information, to store all the information relative to him. Assets in such a model, assets in microstate, are independent from each other. They have independent ownership. This is important, because in a monolithic state design, all those ownerships are mixed together. Everyone can change the state in this contract. Everyone. Right. Why this is important? Because if you consider the design in layers, right? In a layered network, we want to transfer asset between layers. Right? And the basic mechanism of asset transfer is, first I create a proof of withdrawal on this layer, on this chain, and deposit it into another chain. Okay. And independent state means it's easier to create a withdrawal proof. If the states are tangled with each other, all the user states are mixed together, it means after I create my own proof, the other user can touch the state, can change the state, which may invalidate my proof, because my proof is based on the current state of the contract. Right? After I generate a new proof, another user in the ERC20 contract can transfer his tokens, and the state root of this contract will change. It will change everything. How can you keep the proof valid even in such situation? It's hard. But if you have independent state, my state can only be modified by myself. Right? Each user's state is separated, and they will not conflict with each other. Yeah.
So question, so do you want you to have the exactly same structure of the states?
Yeah. Yeah, in my idea, they better have the same structure.
So, but they actually have operating at
different
security
layers.
level, right?
Yeah.
So maybe you haven't talked about consensus, maybe okay, so it's different there.
Yeah, you mean consensus on different layers?
Yeah.
They can have different consensus.
So it's also flexible to people can decide what they want to do on the layer 2.
Yeah. Like on layer 2, you can even have no consensus.
Yes.
It's just a single operator, like
Okay.
plasma chain with a single operator, right? Maybe it's a centralized system. Maybe it's a web service, centralized web service, who continuously generate new state for his users. Or it may be multi-party computation, generate new states together. It doesn't matter what's the consensus on layer 2, but we have global consensus on layer 1.
So the user can also decide under which condition it needs to submit the new transaction to the layer 1, right? The layer 2 as a user.
It depends on the scenario. Like in state channel, right? I want to use the state channel to scale a single contract. So I move all the states of this contract to layer 2 and do all the manipulation of state on layer 2. And whenever I feel okay, I just settle down the state back to layer 1. It's like Lightning Network to settle down payments. So we want to encourage microstate instead of monolithic state. Okay, that's the main technical points, and here's a little about our economics. Okay, we'll have our native asset named CKB. Okay, the same as CKB, but it's common knowledge byte. And you need to pay transaction fee for your transaction because miner did computation for you. Okay. Transaction fee will be paid with CKB, and how much you need to pay depends on the cycles of the verification process. The cycles is gas in Ethereum, basically gas. And what is different from Bitcoin or Ethereum is CKB is also used to pay for state capacity. So, if you want to store something in CKB, you need to have CKB, the token. Okay. And the capacity in use cannot be transferred or used to pay transaction fee. But once you clear, you erase the data, erase the state stored in a cell, the capacity will be liquid again. So the longer you use a cell, the longer you use the capacity, the more liquidity of the token you lose. So in basically you pay state capacity with CKB liquidity. And there will be a hard cap on CKB tokens, which is 33.6 terabytes. By this approach, we want to solve the state bloating problem in our blockchain. Right? Like in Ethereum or Bitcoin, you can keep adding data to the blockchain, and the state of blockchain will increase infinitely. So we add a hard cap to our blockchain state. It's reasonable, in my opinion, because it's not any state. It's state with global consensus. It's slow and expensive. It costs a lot of electricity to create state with consensus. We will give more details in our economics paper, which is writing by Kevin here. It will come soon. I hope. Yeah. And a little bit about our consensus. We use POW, and we are looking for some new hash functions. We are still doing our research. We use POW because it's still the only proven approach for decentralized participation. And POW is good for data availability because the tension between miners, because the competition between miners, which will make them to broadcast their own block, to broadcast new state, which is good for data availability. we will use Nakamoto style consensus, which basically means consensus based on fork, right? And based on forks, we are trying to maximize the throughput of our consensus. I think it's hard to have low latency in layer 1, but it's possible to have high throughput in layer 1. So we are optimize our consensus to use network bandwidth very smartly. And the hint to our solution is the problem to the performance of Nakamoto consensus is every transaction is transmitted 2 times, at least 2 times. One is when the user broadcasts the transaction to the whole network. Right? The other time is when the miner mines a new block, and the transaction will be broadcast to the whole network again, along with the new block. So how can you remove the redundancy? How can you remove one broadcast? If you can do that, you will boost the performance, boost the throughput of Nakamoto consensus. And yeah, we are writing our consensus white paper. It will come soon. Okay. So little bit recap. CKB is a minimal layer 1 designed for a layered architecture, and it fulfills these 3 goals. The first is store of assets. Like Bitcoin is store of value, right? But it's a store of a single value. There are a lot of different values in our world. CKB is store of other values. It's a store of assets. So we want to make it as secure as possible. So that's why we choose Nakamoto consensus with POW and special economics model. Okay, and it's a crypto court which can make judgment based on crypto proofs. That's why we have a crypto-friendly VM. That's why we design our VM that way. And it's layer 2 friendly because we have on-chain state and we prefer microstate, and the natural separation between generation and verification. All those things will make CKB a layer 2 friendly layer 1. Okay, that's it. Thank you. We are hiring.